Welcome to BeeGraphy. In this fifth tutorial, we are going to look at attractor logic. I'm going to explain the concept behind the attractor logic and how we can create a script that incorporates that logic. Now, this is a step up from what we have been doing until now. For example, the twisting tower. We can create one iteration of that twisting tower on any other conventional softwares. Of course, it will take more time, but it is possible. In this case, it's very different. We are going to have a logic, a statement, and then we are going to convert that into an algorithm, a mathematical expression, and that will be reciprocated through our BeeGraphy script, virtual scripting. For example, in this case, we can see that as I'm moving this range input, the sphere is also moving, and according to the movement of that sphere, all the other towers, let's say square towers, are changing their heights. We can evidently see that the towers which are closer to the sphere are shorter in height, and the towers that are further apart, further away, they have higher, taller height. So we can see a logic here, a logic statement. That statement would be the towers which are closer to the sphere have a shorter height, and then as we move further apart, their height should increase. In a mathematical expression, it could be the distance between the sphere and the tower is directly proportional to the height of that tower, right? Of course, I'm going to explain this more in detail while we are doing the scripting, but the basic idea of this exercise, this tutorial, is to open a new door of designing for you. Instead of thinking how to make a conventional model parametrically, we are going to see how to maximally apply and use the possibilities that scripting gives us. For example, this logic, and then creating designs from those logic. This is not something that we do in conventional designing, where the geometries are responding to a logic directly. Normally what we do is we think about something, we think about a design, and then we create spaces conventionally. But here, the spaces will create by the logic themselves, and you will understand what I mean by that. Let's go to our blank canvas. So first of all, we'll have a grid of squares or rectangles, and then we were going to extrude it, and then we'll have another point, and then there will be a component that will calculate the distance between all of them. So first of all, let's create a grid. There are several grids that you can create. Let's do a square grid, and then you can put in range inputs and experiment what changes by what. So I'm going to put in just a random number 8, put that in x count. I'm going to put that same thing in y count to simplify things, so that it becomes a square. So what is x count and y count? It's pretty evident. It is the number of squares in the x direction and in the y direction. If I just have x count 8, then I've got these 8 squares, and then y means the number of rows are only 3. That's the default value. But let's do 8 on both sides. Then you can see that there are some points that have appeared. You can see that there is some space between these squares. So width would control the width of the square, the side of each square, and padding is the spacing between them. So 5 would be the spacing that is there currently. Let's put in 3, or any number you like. Probably space it out even more, so let's put in 10, and we can reduce the width to 10. Yeah. Now, origin would just change the entire position of this entire square grid, but we don't need to change that. You can see that there are two outputs, curves and points. Curve means the red rectangles and points are the middle points. So we are interested in both of them. We are going to extrude the curve and we are going to use the points to calculate the distance with the attractor point. You remember the sphere that I showed you before? We'll call that the attractor point. So let's create a point just randomly. So I'm going to put point, construct point, and our point has appeared. It is overlapping with this one, so put in some number in x and y so that we are able to move it around. Yeah, I can see it now. Also, you can see that when I'm moving the slider, the point is not moving, and if you want to do that, then go to settings and just turn on live calculation. All right, now we can see the point is moving. So the idea is, this is my attractor point and it is going to calculate the distance of all the other points from it, and we are going to use that distance and connect it to the height of each of the towers, right? So let me create line to just explain to you what I mean by that. So what I'm doing is I'm just creating a line with the start point as my attractor point and the end point as all of these points. Okay, so now there is a line that is drawn from our attractor point to all of these points, and you can see that in some cases it is showing an error. Wait, I'll show you. Yeah, here, for example, at 20. So the error is basically the point, one of the point is coinciding with my attractor point, so a line cannot be made, and that's why it is showing an error. So don't worry about that. Just place your point somewhere in the middle and see these lines appear. Okay, now all these distances will be related to the extrusion or the height of each of these towers, right? So for example, if I'm going to extrude this tower, this one, the height of this tower will be somehow related to this line's length, either directly, or we can actually divide it or create a factor, but let's connect it directly firstly. So I'm going to extrude curve. It is asking for curve input, so all of these are these squares, so I'm just going to put it here. So all of these squares have been extruded up by a default value of 10. What I'm going to do is firstly give it a direction, vector z, and then I can put any number here, right? So up it will be extruded in whatever by whatever amount I want it to extrude. What if we connect the distances that we just calculated, the length of all these lines, to the extrusion? So there is a component that can calculate the curve length. So all these lines are curves. If I do this, and we can get all the lengths. You see 74.8, 69.7, 74, 83, all of these lengths are there. So if I connect the curve length, right, all of these lines going into here, into the extrusion z, vector z factor, you can see already we have reached what we wanted to achieve. Okay, so let me quickly show you. So the tower that is, let's say, on this square has a height which is equal to the length of this line that is going from this point to this point. If I change the position of the point like here, then the height of the tower will reduce and become this much. Let's see how much it is now. Yeah, this is the extrusion for it. Even by eyeballing, you can see that it's approximately the same. Okay. Now, in our case, what I've just shown you, the towers were much more gradual. So we can then do adjustments to it. We can cut these tower by half, so we can reduce their height. Let me hide the other things. And let us give it some color material. And also, these are currently hollow pipes, so there is another command called cap, which will make it all solid. I'm going to hide everything else, even cap, and then put it into my apply material geometry. And now if we want to adjust it, we can. Now that this is where the mathematical expressions come into play. So my curve length, all these lengths that are joining the point with all of these rectangles, with all of these squares, is going into the height of these towers. So between this, we are going to add certain mathematical expressions. To do that, there is shortcut. There is something called relay. If you double click somewhere, you can see that the second one is relay. Then there is a panel. Panel allows you to see what is coming out of what is the output of any of the nodes. And remember that if a curve is going in, then this blue one length won't go in. You have to disconnect it, and then you have to connect the length. Similarly with vector, it won't go in. You need to disconnect this, then connect vector, and then you can see all these items. Right, so panel is there, and then this is called a relay. Another way to bring it up is simply double click on this wire. You can see when you hover your mouse over it, and as soon as that finger comes up, just double click and you'll see this has appeared. What this helps in doing is many things. If you've got like a massive script and you're further away somewhere over here, and you want to connect this thing into this also, you can simply double click here and then do this, in case you need to do that. I mean, here it's not necessary, but this is helpful. Otherwise, you'll have to go all the way here and then bring it up, zoom in, zoom in, zoom in, and get it here. So this is one thing that you can do. If you want to connect more items to it, you can do that, like something like this. Of course, here it won't work because this is vector and this is curve. It should be same data type that we studied before. So yeah, relay is very useful. You can play around with it. Here we need a relay to add a function between them. So I'm going to divide. The short for divide is simply a division sign, and then you need a dividend and the divisor. Divisor, let's say it's 2. Actually, we don't need the relay for now, and we can directly connect this here. You see all the towers have been divided by 2. Okay, so the length is going in and this is being divided by 2. If I increase this, and it is being divided by 5, 6, and so on. Okay, so this looks good, and we are almost done. our number, like this range input will control our attractor point, which will in turn control all of these towers. Now, the thing is, this is very simple and of course straightforward. However, this opens the door for you to combine several logics into a script. So for example, in this case, the statement was the towers that are close to the point should be smaller, and then further apart we increase their height. If it is the opposite, the towers which are close to the point should be taller and the ones that are further apart should be smaller. Then you have to play with maths, basically. So let's execute this. Let me showcase this one. So the curve lengths are coming out and they are in this manner. The ones that are closer to it are small, and then the further apart it's large. So what we can do is take a large number and then reduce these amounts from it, right? So if I take a big number, let's say 100, so the tallest tower possible is 100, and from 100 this distance will be reduced, the distance from the point. So this will be the tallest tower, probably this will be 94, and then as you are going further apart, this tower will have 100 minus the length, this long length, so it might be just 10 or 15. So that's how you can do. I mean, this is how I am doing it, but you can do it in a different manner. Probably you are simply flipping this entire list, the curve length that is coming out right now, and this long length is connected to the tallest tower. You can go crazy and say that the longest one should be connected with the smallest, the nearest tower, or something like that. So that is also possible. But let's do the simple one, which is subtraction. So I'm going to subtract from 100, and also, I mean, we can actually check what is the longest distance that is popping up. But even before that, we've got branches to cover. So you see these wires, they are all dotted and thick. If you remember, if there is a single data going through it, then it's a thin line. Otherwise, it is a thick line. We cannot see a thick line here. But yeah, it's a thicker line if there is more than one data item flowing through it. And then the third level is branching. So in this case, when we are looking at the square grid, the data is a bit complex. So if I was going to give you 5 points, like point A, point B, point C, point D, point E, it's very easy to arrange them like A, B, C, D, E. It's a linear set of points that you have, and that data will flow through these wires very simply. It will be a thick line. There are 5 points A, B, C, D, E. But in this case, it's a grid of points. So to make things more manageable, what BeeGraphy has done is they create rows and columns, a matrix of data. So the point is not numbered as 1, 2, 3, 4, 5, 6, 7, and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It's not like this. Because it will be very difficult to figure out what the number of this is. I'll have to figure it out, like it will be 24, 25, 26. And if it is somewhere in the middle, then I have to do like 8 4s are 32, 33, 34, 35, 36, 37. So if it is arranged in a very linear fashion, just numbering all the geometries from 1 to 1000, it's going to be difficult to make sense out of it, locate the geometry, extract the geometry from a list of numbers going through these wires. It will be very difficult to manage it. So what BeeGraphy has done is they've created branches, in the sense, if I tell you this point, you're simply going to count 1, 2, 3, 4, 5, fifth column and fourth row from the bottom, right? So this is much more easier. So this point will be 5, 4. This will be 2, 6 from bottom. Same thing goes through these branched wires. If I'll just show you. So whenever I'm opening this curve thing, you can see we don't have a single list of all points. We've got multiple lists. We've got 8 lists. Each list has got 8 points or 8 rectangles. So these are called branches. Each of these smaller 8 lists are branches. Each branch there are 8 items. I'll show this in a panel. Then there is a concept called flatten and graft. So this is a grafted data structure where the data is not simply a long list of items. It is segregated and put into compartments, into branches. So this is a grafted data tree or data structure. What I can do is I can type in flatten tree, put the same thing into here, and then if I connect it to panel, you will see a long list of rectangles, 64 rectangles. This is a flattened data structure. You can see this has also become smooth. And then there was graft. So if you graft a flattened data structure, you will get this dotted line. But of course, grafting this, what it has done is it has created lists for each of this rectangle, which is not what we want, right? So that's the difference. This is a flattened tree and this is a grafted tree. Why I'm explaining this? Because when we are going to sort the lists, it is going to sort each of these branches separately, like you can see here. It has sorted this branch, has sorted this branch. You see, I mean, it is sorting in this branch, the least number is 100 and the maximum number is 143. In this branch, the least number is 81 and the largest number is 131. So if I want the least number or the maximum number, I'll have to check for each of these branches. Like here it is 62, here it is 43, it is 25. So we need to flatten it, get all these numbers in one sequence, 64 numbers, and then arrange it so that I can get the minimum and maximum quickly. I'm going to type in flatten, and then we'll see what happens. Now we've got sorry, we need to put in this here. Then we take the flattened tree into the sort and then we will check the panel. So now the least number is 9.4 and the maximum is 143.555, right? Actually, we'll just put our point in one corner so that we can get even larger tower. That's 185. So I'm doing this so that I can select the correct number to subtract from. So 185. So let's take 200 as the minuend. I'm going to put max as 200 and select it, put it here. And then I'm going to do 200 minus the number we were putting in the extrusion right now. So let's do that. And then I'm going to use this as my extrusion factor. Okay. Oh, right. Because okay. So we are dividing it. If I don't take the division, if I just directly take the curve length, then it will be very close. Yeah, like this. So it is 200 minus 185. So this tower is 15 units high. All right. So now the logic has reversed. Basically, that if this is the logic I wanted to apply, this is how you play with the mathematical expression, and then do the scripting like I've shown you to modify the script, to modify your logic. Then you can play with all of these things. And yeah, if it is too less, then the towers will go inside and opposite side. That's why I had to look at the maximum number, this 185. So that I can select 200. And just to check, the towers which are closest to the point will be the tallest now. I don't know if you can see it. The point is here where there is the highest tower. You see? And this is responding as expected. And then of course you can divide this entire thing as you want, but I would do it like this. After subtraction has been done, then I am putting it for division. And let me just hide this. All right, so I think this is good for this tutorial. In the next tutorial, we are going to see how to combine several logics to our attractor, one of the attractor logic. So in this case, it's just a point, and the height of the tower is connected to that point. So the next statement would be, what if I want the size also to be changed? I want it to rotate according to the distance from that point. And this is useful when you are stating certain logic, such as you are creating a facade and the shape of the facade should respond to the sun path or the incident radiation on the building. So you can do some solar analysis, do some simulations, and then on the surface you get different data points where it is where too much sun is falling and where very less is falling in. And then the apertures, you can say the apertures are larger in the areas where less sunlight is falling, and they are smaller where there is too much sunlight going in. And then you will get something very interesting form, which is aesthetical, but more than that, it is precisely according to the logic that you've just stated. So that is just one of the applications of attractor logic that we have here. So hope this was helpful, and see you in the next one.